Okay, so now we have been discussing about spatial instability, and in the context we were looking at the finer details that within the spatial instability problem itself is a possibility that time dependence exists, and that is what we were doing in this part of the course, where we are talking about spatiotemporal instability, and we were following the Bromwich contour integrals. And in the Bromwich contour integrals, we just looked at a few representative points. We performed the Bromwich contour integral along two contours in the wave number and the circular frequency plane, and we investigated 4 representative points. Point A corresponded to an unstable scenario. Point B corresponded to the same Reynolds number, but significantly higher circular frequency, whereas point D corresponded to the same Reynolds number, but significantly lower frequency, and C is a point which is a subcritical point, that is this is for a Reynolds number of 300, while the other 3 cases are for Reynolds number of 1000. And the fact that point A is unstable is represented by one of the negative alpha I, whereas rest of the modes are seen to be positive. We talked about the group velocities. We also talked about the signal speed, right. Signal speed is what Sommerfeld started talking about. And finally, we did talk about the energy propagation speed. This was what was proposed by Brillouin, and in this context, we started looking at energy based receptivity theory. Please do understand that I emphasize that this is a energy based receptivity analysis. This is not a your stability analysis. Why did I say that? Because your governing equation for the disturbance energy that we have written here in Fourier Laplace formalism is governed by this equation, and this equation came from here, del square E d, which is some function of the mean vorticity, the disturbance vorticity, the mean velocity, and the disturbance velocity, right. And when you look at it, that there is a distinct forcing for this case, unlike the Sommerfeld equation. Sommerfeld equation is homogeneous. This is an inhomogeneous equation. So, this is the forcing term. So, once you solve the Sommerfeld equation, you can see for yourself what drives the energy. And if you look at the corresponding homogeneous equation, that is nothing but the Laplacian. And we know that Laplacian does not exhibit any instability, simply for the reason that this path does not have any time dependence. If it does not have any time dependence, then of course, you can't talk of its instability. So, what instead we are talking about the receptivity. So, if I prescribe some kind of a disturbance in the flow field, that will create the vorticity field, that will conspire with the mean flow to give this kind of a forcing on the energy. So, this is something we must keep in mind when we are talking about energy based approach, that this can at best be a receptivity analysis, can be a stability analysis. Okay. So, what we did was we performed those integrals for those 2 points. The one below is for the unstable frequency of omega naught equal to 0.1 for a Reynolds number of 1000. The result that you are seeing here is at a height of 0.278 and at a terminal time, which was allowed by the string of data that we took, is given by this. And what you notice here is a sort of asymptotically growing solution merges with the leading edge of the wave packet. So, here the existence of the spatiotemporal wave front and the asymptotic part of the solution are not distinct, while that is distinct for the stable case. For the stable case, what we see, of course, the asymptotic part is decaying, but the spatiotemporal part, which actually grows in space and time, continues to be there, and you can see them very distinctly. If we would have aligned these two figures properly, we would have seen that they would have matched and they would have been the same. And this prompted us to comment in the last class that this is perhaps a very strong function of Reynolds number, and these two are for the same Reynolds number, but for different omega naught. But the spatiotemporal solution is being a function of Reynolds number alone, and these two being same, they have an identical structure. So, this is what we commented, but at the same time I also made the observation that this needs further probing. So, basically in summarizing it, we are basically talking about the same thing, that when we are looking at the ED variation with x, we see that that is much more smoother than u. The reason is E has that v square by 2. E has that v square by 2, and well, I mean, this is not a quite a carefully made statement. What we are saying that we do not have a detached forerunner. We are not saying that there are no forerunners. So, please do understand that there is a detached forerunner, while for the point B you can simply see the distinct detached forerunner. The rate at which this asymptotic part as well as the forerunner propagates can be roughly estimated from the figure itself. We have a visual signature, from there we can calculate this. And this was what was shown in the last column of the table. We just opened up mode 1, that is that unstable mode. Okay. And it just so happens that if you do a Fourier analysis of this forerunner, that corresponds to the second mode in terms of the wave number alone, because you see the second mode is a stable mode. However, what we see in our calculation, we have calculated all the way up to 800, and the spatiotemporal wavefront kept on increasing. So, it is not a decaying thing like the second mode. So, even if I say that in terms of wave number it matches the second mode, it could be just pure coincidence. Okay? So, it is not a causal factor. And what we found that when we are looking at stable system like the point B or D, what we find those have multiple modes, and the forerunner has identical the energy propagation speed as well as the signal speed, and that lies between the group velocity between the values of the leading modes. For the stable system, if we have a single mode alone, we do not see the forerunner. That case also, once again I emphasize, was for r equal to 300. So, maybe it is such a strong function of Reynolds number that for r equal to 300 we do not have a forerunner. So, there is a distinct need for performing this kind of analysis for different Reynolds number and see how this forerunner behaves with time. Let me now go over and talk about a new thing. What is the new thing that we are talking about? We are going to talk about completely a different aspect of instability. Now, there are two things that I want to highlight here. Number one that we are looking at here is here we are not anymore talking about spatial instability. We are talking about systems which display temporal instability. And once such an instability is there, this is going to be distinctly different from spatial instability. In the spatial instability, what happens? The disturbance washes off, it convects away. And if we do not take a very large domain, we do not get to see the disturbances growing very much. That is more a sort of a limitation of our computational domain. If we probably would take much longer domain, then we could see that it is growing to much longer time, like exactly what we just now finished our discussion on, that if instead of taking 512 points in the omega plane, if we would have taken let us say 8 times or 16 times more number of points, we could go over for much longer time. And then if we also take a larger x region, we would see that the asymptotic growing path will keep on growing, because it is a linear theory. Linear theory does not tell you where to stop, it just simply tells you it is unstable, that is about it. So, that is the second part, that when we have such an unstable system, then what does nonlinearity do? We clearly understand one thing. I suppose you will agree with me full-heartedly when I say that the disturbances cannot grow completely unbounded. Why do I say that? Because the energy for the disturbance comes from the mean flow. Mean flow has a finite energy. So, disturbance quantities cannot grow unbounded. In fact, the very phenomena of transition from laminar to turbulent flow tells you something about moderation of nonlinearity coming into picture. The linear theory or the instability theory says the disturbance grows. Where does it stop? That is the nonlinearity comes into picture there. So, in the second part, what we are talking about? We are talking about temporal instability, and we are talking about a finite domain. And if such a system is linearly unstable, what am I going to see? With time it is going to grow forever. And if I am doing real time plane calculation, not in the frequency plane, not via Bromwich contour integral, suppose I keep on doing for large time, what will happen? It will eventually blow up. Computationally though, for various systems that have been studied which display temporal instability, we do not see such a thing. And one of the best examples for this case is a flow past a circular cylinder, a blob body flow. So, we are basically next talking about blob body flow instability. If we are talking about this, people tend to think that this is entirely a different phenomena altogether, does not belong to stability study, but they try to always approach this problem from the point of view of solving the full nonlinear equations, the Navier-Stokes equation. What do we see? Let us first of all identify what we see, and then we should go about understanding what is going on. Let us say we have a flow, uniform flow approaching this blob body. Then if I focus my attention on a particular point in the wake, what am I going to see? I am going to see something like this. If I plot the disturbance velocity, what I would see that initially it remains so, then it slowly builds up, and once it builds up, it indicates some kind of a growth in time. When it shows the growth in time, natural question that arises in our mind, that will this growth be forever? But what we notice that it does not happen so, it actually saturates. And this is where our present discussion starts. We are talking about effect of nonlinearity, and this effect of nonlinearity was studied initially by Landau, the famous Russian physicist, and he conjectured, he produced an equation which is called the Landau equation. Which will tell you about the amplitude of the growth of this disturbance, and that kind of tells us that why and how this growing amplitude saturates. Okay? So, this is what we are talking about. This is related to another phenomena which is often studied in mathematical physics, namely the phenomena of bifurcation. Bifurcation means what? Now, this is also where some amount of misunderstanding prevails. Supposedly, I call this modulus here as A. Then what we are seeing that this A is a function of time, but because of the mediation of the nonlinearity, I get a saturation amplitude. This I call it as AE, equilibrium amplitude. Now, what I could do is I could plot this equilibrium amplitude versus RE. I could do it experimentally, I could do it theoretically or computationally, and I can measure it AE as a function of RE. What I would see that up to some Reynolds number, this equilibrium amplitude is 0. What does it mean? The system is linearly stable. So, this kind of instability does not arise for those Reynolds number. Then after that, slowly this disturbance, this instability starts. There is an onset of instability, and with the increase of Reynolds number, this equilibrium amplitude keeps increasing. And Landau proposed an equation which shows that this equilibrium amplitude goes like this. So, it is like a parabolic variation, AE versus RE, and this point is the point where we have the onset of instability. So, what we are saying then, on this side we have linear stability, means if I perform a stability analysis, linearly it is stable. On this side, what I find, linear stability, instability plus a nonlinear saturation. This is the part that we need to understand. So, the point at which the instability first appears, what does it tell us? That if I am looking at an arbitrary Reynolds number, then there are two possible solutions. What do these two solutions imply? This is what we are seeing there. This is what we have plotted. What does this imply? This implies there is no growth. How can it happen? Since we have studied so much on receptivity, you can give me an answer by saying yes, it can happen. Suppose I do not have the corresponding input, I will not see the output, right. So, it is basically this, that I can get this solution or that solution. So, that means the system from this point on bifurcates. It can have two solutions, one undisturbed solution, and there is a disturbed solution. So, this point at which this thing starts is what is called as point of bifurcation. So, system bifurcates. In fact, you know, most of you have some exposure to various other aspects of fluid dynamical flow, including let us say aerodynamics. here if you realize that if I am talking about a flow past an aerofoil which is at an angle alpha, then what I can do is if I increase this angle of attack and measure the lift coefficient, I see that it goes like this, then it has a stall. But now suppose I reduce the angle of attack, what happens? It does not follow this, it comes on this. And you know that if I go on the other side, I could have a similar scenario, but then when I increase it, I again may not go along this. So, I could get this kind of a picture. What is it called? Of course, you all of you know it is called hysteresis, right. So, there are many examples of physical system which shows hysteresis, which tells you what? That for a given angle of attack, you can have 3 possible solutions, and which solution you belong to is dictated upon the rate at which your angle of attack has changed. If I started from angle of attack 0, I would be on the middle branch, but if I would have come to the same angle of attack coming from a stall angle, then I will be here, and if I go back and again retrace the cycle and now again I am on the increase, then I will be here. So, this is basically 3 possible solutions, and here we are talking about 2 possible solutions. Well, this is a clear example of flow phenomena which tells you the dependence of the flow on the time history, isn't it? Where we have started, how we are going through that state. This is what dictates whether I am going to be on this branch, or that branch. Here, the thing is slightly different. What it says that if I am working on this Reynolds number, then of course, I can have this unstable solution, saturated solution, disturbed solution, but I can also have this depending on whether I have the corresponding input to the system or not, right. So, please do understand that this is what it is. When this breaks up, the solution goes up like this, it is at a quadrature. This is what is called as Hopf bifurcation. So, that is your Hopf bifurcation. There are other kinds of bifurcation like pitchfork bifurcation, etc. We will not talk about them. We will keep our attention focused on blob body flow instability, and then we will see where do we go from here. Okay. So, basically when we are talking about nonlinearity, effect of nonlinearity and going to another saturation amplitude, etc., what we are talking about? We are actually talking about a linearly unstable system that goes to another equilibrium state. That is what happens here, that we do get this vortex shedding pattern, Kármán vortex treat. That is basically that, the next equilibrium periodic state, right. A vibrating pendulum, oscillating pendulum is also an example of equilibrium state, and that is also a consequence of what was your original equilibrium state for a pendulum, to remain vertical in one place. You have disturbed it, then it keeps going back and forth, and there is a trade off between the cause and response. You see what happens? We see basically a disturbing force, that is the kinetic energy and potential energy does a perfect balancing act, and you get a constant amplitude oscillation. That is your pendulum. It is also the same thing here, vortex shedding behind a circular cylinder. It is like a fluid dynamical pendulum. Do you see the connection? That here instability starts off, which we have in the linear mechanism, then the nonlinearity starts coming into play. That provides a kind of a saturation to it. We will see it. We will shortly come to the Landau equation, and there is a perfect balance. And you come to this from a one linearly unstable state to another equilibrium periodic state. Okay. This is of course not generic for all flows, but it shows up very graphically in flow past bodies beyond the first critical Reynolds number. Now, this is the first critical Reynolds number, and I am, well, we have actually by now. When this visuals were created 2 years ago, we were in the process of working out, but today we can very confidently say the work is done, and we have shown that there is no such thing as a first critical Reynolds number. This again is built into this picture, that whether I can remain here or I can remain there. So, I will get this bifurcation when I have that class of disturbance. Then I could actually consider a fluid dynamical system where this first bifurcation does not take place. If this is bypassed, then I can continue to be here, and then I can actually go to the second bifurcation. In fact, that is what we talked about in the title itself. When we talked about this couple of years ago, people were not very sure what we were talking about. What is this multiple Hopf bifurcation? People were only talking about Hopf bifurcation, and here we come and we say, look, I mean, there need not necessarily be a definitive single bifurcation, because that is what this bifurcation diagram clearly shows. I can bypass this first critical point, but then there could be another class of disturbance which triggers a second bifurcation, which can trigger a third bifurcation. And let me just tell you what you are going to see in advance in this course, that we have now established a scenario where you would see multiple Hopf bifurcation not only for this external blood body flows, we have also shown it for internal flows. Wherever we have vertical flows, we have shown this. We have made a claim in one of our very recent work paper, which is in the press. There is a universality of this picture. So, keep that in mind, and then we will go along and we will see how the drama unfolds. So, what we are saying that for flow past a blood body, we can very graphically see this. Whenever we cross first critical Reynolds number, and if there is sufficient disturbance in the background, we are going to see this. There is no doubt about it. But there was this experiment done by one of the students of Ludwig Prandtl, Fritz Hohmann. He did this experiment. He was very clever, far ahead of his time. What he did, he created a recirculating tunnel, like what we have, the wind tunnels or water tunnels people do talk of. But Prandtl probably suggested to him, or they thought together and came out with the idea that they will build a tunnel with a completely different working medium. They used lubricating oil, which has a very, very high viscosity. And then in that recirculating tunnel, they put in a circular cylinder and did the experiment. And their experiment showed that there is no vortex shedding up to R equal to 65. So, Homann's result showed a Re critical close to 65. Now, if you look at the literature of 80s and 90s, there was a nice bandwagon. Everybody said Re critical was 45 to 47. And people said this based on computation. So, this is another example of abuse of computers. People ganged up together and made a lot of hue and cry, saying that flow past a cylinder, critical Reynolds number has to be between 45 and 47. And here was this result. Well, it was not published per se, but it was a thesis. And people did know the result, because those visualization results are in Schlichting's book, are also in White's book. So, two of the best known fluid dynamics book featured those results, but nobody was willing to reconcile between these two. Experimentally, you could go as high as R equal to 65 and have no vortex shedding, whereas here was another set of people who were determined to say that there is a universality, and this critical Reynolds number is about 45 to 47. Right? Now, where is the truth? Truth is of course colored, in the sense various other experimentalists have come out with different estimates of Re critical. For example, if you look at the book by Landau and Lipschitz, they did not show any documented results, but they claim that the flow past a circular cylinder becomes unstable for a Reynolds number as high as low as 30 itself. Batchelor's book also talks about, which also contains Hohmann's result. Batchelor's book also talks about critical Reynolds number somewhere around 40. And there are any number of people who have done experiments, they talk about critical Reynolds number of anywhere between 40 and 55 and so on and so forth. But no one actually goes this high. And I explained to you why this high value was achieved. If you are working with a media of highly viscous fluid, then what happens is that if there are any background disturbances, they are damped because of the viscosity of the medium. So, that was the unique thing, and it was only in a paper which we published in the last couple of years, we have shown the connection, what could be the reason. One thing is for sure, existence of the bifurcation diagram very clearly shows the role of receptivity. We cannot escape it. If we do not have the input disturbance, we are not going to see the response. And that is what all these authors, all these experimentalists are talking about different Re critical from the same point of view. And to talk about an universal critical Reynolds number in the range of 45 to 47 is a bit far-fetched. Okay? So, what we are going to do now, we are now going to see what really happens in this flow, and what was this Landau equation that we are talking about. Landau equation was conjectured by Landau. He did not actually give enough steps in his work that how did he come to that equation. Later on, this British mathematician J.T. Stewart, he did a very good bit of analysis with the help of Watson's result, and he showed that Landau's equation actually comes about from the stability equation itself, instability equation itself. The nonlinearity comes from a self interaction term, and that was a very good reason for showing the validity of Landau's equation, right. So, Landau equation, although was written in a heuristic manner in 1940s, it took another 20 years before it was formally shown how it is to be. So, that is why today we call that equation as Landau-Stewart equation, right. See, the issue that we are addressing here is one of instability, but when Landau proposed his equation, he was more interested in explaining how turbulence comes about. What is the scenario he was talking about? That you have a primarily unstable flow that leads to temporal growth of disturbances, nonlinearity comes into play, and you get into another periodic state. That is your first bullet. Now, once you have arrived at an equilibrium state, altered equilibrium state, that is also susceptible to disturbances. So, what happens? That could suffer an instability, that would be a secondary instability, and that could lead to potentially another equilibrium state that can suffer another instability, and so on and so forth. So, Landau's viewpoint in proposing this equation was that we are talking about such successive bifurcations, an infinite number of such bifurcations, or a very large number of such bifurcations, which leads a flow from laminar to turbulent state. So, he understood the turbulent state has finite energy. So, it has to end in some equilibrium state. And you also realize that what is going to happen if we are talking about instability of an equilibrium state. The primary flow, the first instability could have been on a steady flow, right. After the primary instability has occurred, what is the flow situation here? This equilibrium state is time periodic. So, a mathematical theory was developed quite early on. It is called Floquet analysis. Okay. Floquet theory. In Floquet theory, what you do, you study the instability of equilibrium state which is periodic. So, in a sense, what Landau was basically suggesting is a kind of a primary instability followed by instability of periodic states, and going from one periodic state to multiple periodic state, and instability of multiple periodic state, and so on and so forth to turbulence. So, that was his scenario of turbulence. It is just a matter of record. It is a bit of a storytelling here, that in the 60s people did come across what is called as chaos theory, which showed that some of these flow phenomena that we usually study corresponds to very high Reynolds number, and these high Reynolds number flows are susceptible to small disturbances. And some of the mathematicians came out and talked about what is called as sensitive dependence on initial condition. And in particular, Feigenbaum want to make it little more dramatic, and he started talking about that so called butterfly effect. The story goes, according to this anecdote, is that systems are so susceptible to small disturbances that if a butterfly flaps its wing in Europe, it changes the weather in America. So, it is a kind of a bit of a story. You want to sell it on a news magazine or coffee table thing, whether it is nature or science, does not matter. You have to shock the people, you have to give them some of this bylines which sells. So, this butterfly effect and all these things came about. Now, the question is, following those ideas, people found out that if you decompose, let us say, Navier-Stokes equation, if you decompose Navier-Stokes equation in using Galerkin projection, then these truncated models are shown to have this kind of properties, and this is where you may have heard of Lorentz. He was a meteorologist working in MIT, and he came out with this, and he basically produced some solution of Navier-Stokes equation where it was truncated to 4 modes, and he showed that this 4 mode system was very susceptible to disturbances, and this chaos was interspersed by period of quiet. So, you have in the parameter space, you have quiet flow followed by chaotic flow, then again quiet flow, again chaotic flow, and this kind of things happen. And there were other mathematicians who came along, and then they said, look, you do not have to wait for this infinite sequence of instabilities as was proposed by Landau. They said 3 such bifurcations are good enough to take you from laminar to turbulent flow. So, this was the kind of scenario with which we have grown up in the last couple of decades, and it is very poignant because people also tried to show this with the help of fractal nature of turbulence, and this is a weak Mandelbrot just was one of the pioneering mathematician who worked on fractals. He just passed away. So, it is kind of a scenario. I am just trying to give you a big picture where we stand today, that there were lots of this to and fro's have gone in, but please do understand that our approach to this discussion that we are talking about is rooted to instability. We wanted to show what instabilities are for unstable systems, fluid dynamical systems, and as far as this phenomena is concerned, or which is shown here, what is the role of nonlinearity? Here the role of nonlinearity is not accentuating instability, it is moderating the instability. So, that is why effect of nonlinearity here is one of moderation, not of destabilization. Now, Landau actually were interested in trying to explain flows which are known to be either completely stable like Couette flow or pipe flow, we have talked about it, or let us say in a channel flow where the critical Reynolds number is known to be about 5772, but you do the experiment as was done by Davis and White in their preceding and Royal Society paper reported work. They found the flow in a channel becomes unstable as at a Reynolds number of as low as 1000. So, there is something that some of these flows suffer instability while the linear theory says they have to be stable. So, whatever we see, that should be called as the subcritical instability. So, Landau was developing this theory to explain subcritical instability, but we explain only here the supercritical stability, right. This is a case of supercritical stability. So, you are working on this side, right. So, flow has already become unstable because you have crossed this Reynolds number. So, you are on the supercritical side, and then nonlinearity actually saturates the amplitude. So, that is what we are talking about. So, with this brief introduction, I think we can go ahead and develop the Landau equation. What was done in Landau's equation is that if I am looking at the linear stability theory of steady basic flow, then we know by now that we create a large spectrum, right. So, the modes, let us say they are independent, and then with the help of those modes we can reconstruct the velocity perturbation in terms of this. This is your Galerkin projection, a time dependent function times a space dependent function, and we add the complex conjugate to make the whole thing itself as real. Okay. So, this A star F star are nothing but the complex conjugate of A and F. Okay. So, this is the usual way that we do. Now, the complex amplitude, when it has become unstable temporally, we could write that A of t is some multiplicative constant times e to the power s j into t. So, what we are looking at? We are looking at the jth mode, and that has a growth or decay rate given by this complex exponent s j. Now, if this is the expression, then I can differentiate it with respect to time, then I will get d dt of a j is s j j. This is what we will expect. Okay. Once I find those growth or decay rate as eigenvalues, I can also correspondingly find out the eigenfunctions, and we can identify those f j's with those eigenfunctions. So, starting from a linear theory, I could get the growth decay rate, I could get the eigenfunctions, and I get this. However, this is your linear description of the system, right. What happens is we can obtain a corresponding nonlinear systems and use the same kind of Galerkin approximation, and we would be able to show that the evolution equation means equation with respect to time, differential equation with respect to time for the amplitude a j would be given like this. So, this is your linear part, this is the additional nonlinear term, which we have symbolically written as n j, and remember now we have a large number of modes. I have written here infinite, but you have already seen for Blasius flow it just so happens you have only 3 such modes. So, it is not necessary that you will have to write it up to infinity, it is just for sake of completeness. Now, what happens is the jth mode not only depends on the growth or decay rate of the jth mode from the linear stability analysis, but it can be also affected by other modes. And if you think of your Navier-Stokes equation, where would this term come from? This term would come from, let us say, something like your Reynolds stress like term. So, there you can see that different modes can interact, and that is the source of this. That is what we are saying, the nonlinear effect on the jth mode created by all possible kth mode. Okay. So, this is the general formalism or ansatz we can talk about. Now, this is where Landau did his magic. Landau said that this n j of a k does provide the nonlinear action of all the modes on the jth mode, including self interaction. The mode by itself can interact with itself. So, what Landau suggested that this n j of a k is equal to a j times mod a k square. Okay. However, if we now talk about only a single dominant mode, like what we have seen for all the cases, flow past a flat plate, we had a single mode which dictated the dynamics. Then what happens is this could be only coming from a j times a j mod square, and then I will have this kind of equation. And there is this multiplicative constant L by 2. Please note that this S that we obtained from linear stability theory, we are looking at temporal instability. So, it will have a real part and imaginary part, right. Same way this constant L also will have a real and imaginary part. This L is what is called as the Landau coefficient. Okay. And what we could do is we could substitute this S and L expression here and obtain the evolution equation for the amplitude squared. Okay. This will be like this. So, this is what was given in Landau's paper. He did not say where he got this equation from. He just simply said the nonlinearity is such that it would be like this, because he knew that this equation has a closed form solution. And we will talk about it in the next class in greater detail, but whatever we are describing here, this was very nicely elaborated by Stewart, and later on this is given in that monograph by Drazin and Reed. You can read that. You can also read the lecture notes that I have written, where we have shown how we get this equation and we make this assumption that there is a single dominant mode, and then from there we get a I could write it in terms of in the polar form, right, r e to the power I theta. The r itself I will call it as mod A. So, then the governing equation for r will be like this and governing equation for theta will be like this. Landau actually completely missed this part. He never mentioned this. In fact, he wrongly said you cannot even predict the phase. He just simply said you can at the most predict the amplitude, and the equation would be given somewhat like this. So, I think this is where I would stop today, and we will begin from here tomorrow, right.